Okay, good. Okay, so what I'd like to do is, the problem of the day is a backtracking problem. And I want us to think about this one just to get more insight into things. It says that multisets, okay, are sets that are allowed to have repeated elements, okay? And a multiset of n items might have fewer distinct permutations, okay? So a permutation, remember, is an arrangement of things, right? A multiset, if normally we think about permutation as n things being made up of n distinct items, right? The numbers 1 through n, okay? What if we want to say, I'm giving you a certain number of each item, and I want you to construct all possible arrangements of n things using exactly those items? Does everybody see that if I give you the items 1, 1 through 2, you might say, there's 4 factorial permutations of that. There's 24 distinct permutations. Does everybody see that if I have duplicates, that's not true, right? In fact, according to this, it says that there's only 6 different permutations, okay? So if I give you a multiset, a set of n things where n things are all distinct, there's n factorial arrangements. Does everybody see that if I allow duplicates, there can be far fewer arrangements? Can someone give me a set of n items such that there is only 1 permutation of these items? Yeah? All ones. If I give you all ones, does everybody see that you should output only one thing? Okay? Any questions about it? No, 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 no. No, no, no. No, 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 no. Okay? Any questions? Okay? So how can we go about doing this? How do we use backtracking for this? Okay? What is the first thing that we need to do?
So obviously we start by just putting all the possible elements in the first and then branching.
Well, okay, but I say, what do we need to do? The first thing I think I want to do, what is the first thing we do?
Define permutations.
You say, what?
In general, define all permutations.
Okay, so you're saying that the simplest way to do it, okay, is to construct all permutations and then do something of them. That's what I think you're saying.
Well, construct an algorithm that finds all permutations and then adjust the algorithm slightly so that you prove it.
Okay, maybe. This is still not the first thing that I would be doing, yeah? Okay, first thing I would be doing is define what my solution vector is. Okay, and what is my representation of what my problem is. Okay, so how am I going to be representing a solution? Okay, yeah?
The most naive way would be to have an array and give just the permutation, but a better way would be to have an array of all the items and link this to something inside of all the positions there.
Okay, so I think what we're saying is we're sort of agreeing that my solution vector is going to be the permutation as I build it. Okay, that I now understand. And what you may be saying is that you want some other data structure to help me make some decisions about it, about what I should be doing. Okay? So what should I do to lay out this thing? How would we go about doing it? Again, we've got our 3 magic things we need to do. We've got to give a construct candidates, do we have a solution, and process solution. And with all these problems, there's different ways to spread the work. How would someone want to try to propose a way to do it? Okay, you.
So use a standard algorithm for generating all permutations of an array and change the construct candidates part to only swap with one element once. You don't want to swap 2 indices that have the same element.
Okay, I'm hearing swap. I don't know what the word swap means here. But what I think what you're trying to tell me is we're going to build this up as let's say our partial thing looked like this. The key question is, what are the candidates for the next position? Okay? And what would be the candidates for the next position? Yes? Okay, so I'm hearing the word counter how many times? Okay, so now let's say now I sort of understand the following. Let's say I have an auxiliary data structure telling me the input is going to tell me how many things there are, right? So if 1, 1, 2, 2 tells me that there are, if I was building, let's say I'm going to try to do this one, right? There are a certain number of 1s and a certain number of 2s. Initially, there were 2 2s and 2 1s, right? Does everybody see that? Let's say we first put down a 1. That's going to remove one of these guys, right? Does everybody see that? How many remain? What are the candidates for the next slot? If we have to construct candidates, what are the candidates for the next slot? Yeah? 1 or 2. And why is it 1 or 2? Okay, how do we know whether, so you're saying this is a 1 or a 2. Does everybody see that? Now, if I put in a 1, what is going to happen here? My 1 availability is now 0. Does everybody see that? So what are my candidates for the next spot? It's only 2. Does everybody see that? And once I put the 2 in, now there's only, what are the candidates for the next spot? Only 2. There's going to be no more after that, right? And so since this is done, it's going to backtrack, 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 replace this by a 2. And now if I've got a 1, 2 here, what are my candidates for the next position? 1 and 2. Does everybody see that what the key thing here is? I am going to keep track of how many available copies I have left of each element. And I am going to put down my candidates for the next position are any element that there is at least one element, one copy of it remaining. Any questions? Yeah.
Do we have to store the possible candidates every step so we make sure we don't have duplicates or no?
Do we have to store the possible candidates at each step? I don't know what that means. Because if we think about what my backtracking routine did, construct candidates, returned an array of the candidates for the next slot. Does everybody see that? So certainly we need to return it. But the candidates here would be either 1 or 2, 1 and 2, or 1 or 2, or none of them. Okay? Any questions? Yes? So I would have to, again, how would I implement this? Okay? So one possibility is, that was a rhetorical question, how would I implement this? One possibility is, and again, there's different ways you can implement this that are going to be essentially the same thing. It's a programming approach. One possibility is I keep the original global counts, okay, how many 1s and 2s, and I keep these fixed, and I'm never going to change them. And then, when I try to compute my next element, I am going to count how many times I have used each element so far. And then once I have those counts, I can subtract it from these to figure out if it's which ones are 0 or not. Does everybody agree? So there's different ways you can do the bookkeeping, right? You could either keep kind of maintain a count of how many things are how many spots are available in the current array, and adjust that every time I increment or every time I move forward or backtrack. Alternately, I keep a global count of how many things I had in the first place. Then to decide the next position, I go through my prefix and do the checking. Okay? Any questions? Yeah. Okay, I'm not quite getting. I'm not. Say that again, because I'm not understanding it.
The way I was thinking of doing it would be sorting the input vector.
So sorting the input vector had the property of giving me 1, 1, 2, 2. You mean the input vector or the partial solution?
Input.
Okay, fine. Yeah.
And then in construct candidates, you'll have
the last a sub I, meaning the last value I set, okay, yeah, which was this.
And then you would check to see that in the next I, that it's a different value.
No, there's nothing wrong with having the same value, okay? So notice there's no reason why I can't have a 1, 1 next to each other in one of these things constructed, okay? So I'm not sure I'm getting at what your idea is, but the way I'm thinking about it is this is bookkeeping. Does everybody kind of see that trying to figure out how you figure out whether you've used all your 1s or your 2s is a bookkeeping programming thing, right? And that doesn't seem like that should be rocket science, right? The key step criteria here is to note that all we have to do is put down any element that has not been completely used as a possible candidate. And if we do that, we will get all the permutations. Yes?
So I just have curiosity. In general, if I'm working on a hard problem, I shouldn't really be worried about the order complexity of the bookkeeping, right?
Okay, so the answer is, should you worry about things on the bookkeeping on a hard problem, on an exhaustive search kind of a problem? My guess is to say that there's the way I would think is that there's different levels of worrying about things. Okay? So it should be clear that, that the biggest thing driving the correctness, the speed of something like that is how fast you're going to be doing, how good a job you're going to do pruning, right? Now, that said, does that mean that I should throw away all caring about data structures and stuff like that? You know, I would say no. You know, you've learned a certain level of hygiene in data structures, and it should bother you personally that you're recomputing something you don't need to be recomputing, right? I am sitting here, you know, was trying to be nice and open-minded to you guys who said, oh, should we recompute the whole sums now and then subtract it rather than maintaining the counts? In principle, maintaining the counts dynamically is going to be faster than recounting every time you go through it. Now, how much faster will it make it? Might it make the program twice as fast? 3 times as fast if you have the better data structure? Is that worth it? Okay. In general, if I can make my program 3 times faster, is it worth doing? The answer usually is yes, right? So the way I think about the pruning is the first order thing driving it. But you guys, you know, it's good practice to be thinking, how do I use data structures efficiently so I don't, you know, the total amount of time is going to be the number of states you visit in this backtracking times the time you do at each state. Does everybody see that? If I spend twice as much time at each state, the program's going to run twice as long. If I spend the same amount of time but visit twice as many states, it's going to take twice as long. Okay? So most important for you is pruning, but you know, but one should remember what we know about data structures and do the right thing. Any questions? Okay? Because sometimes, frankly, once you do the right thing, that suggests also, you know, it suggests other kinds of transformations later. So that's, I guess, my sense. Any questions? Is there any other way, other than by changing construct candidates, we could have done this problem? Yeah? Used a bigger data structure to store them. A different data structure to store them. Let's say I don't know what that means. Not data structures, big rearrangements of how we would do the search, yeah?
So as I imagine the problem, I started out by just computing every single permutation, and then I adjust the algorithm to say, okay, at each level of recursion, let me keep track of all of the unique things that I've already inserted into this particular position, and if I encounter it again, I ignore it.
Okay, so one idea that is sometimes done, that is often, you know, of shady use, maybe what you would do is say, I'm going to construct all permutations, okay, and then test them at the end, okay? That would be bad if I constructed all n factorial permutations, right? But maybe a little bit less bad would be to go through and do backtracking ignoring the distinction of the elements, except I build a hash table of every prefix I have ever worked with. Does everybody see that your search is being driven by what prefix it is here, right? And if I have already evaluated that prefix someplace else, I don't need to evaluate it again. And you could use some kind of, I think this is what you're kind of saying. Okay? You use some kind of a data structure like a hash table to keep track of what states you have seen before to stop, so that you don't search from it again. Okay? And if you can do that, maybe that's good. But note that if you're doing a real depth-first searchy kind of thing like this, we're avoiding ever seeing, with what I'm doing with these counts, I'm avoiding ever seeing the prefix more than once. So I don't need to do those kind of tests. Any questions? Yeah?
How long does the prefix have to be for it to tell if it was?
Well, if somewhere along the line I had started doing a search, okay? And again, I don't want to make this too complicated, but if somewhere along the line I had done a search from 1, and later on, for some reason, I again do a search where this is my prefix. If I've searched all possible implications of this, I certainly wouldn't want to try putting a different 1 ahead in the first slot and try again, right? Does everybody see that? So if I had just hashed on this, and this, when I hashed on this, I would say there's already one of those in the table. This must be a different copy of the same thing that I did there. Okay? Any questions? Yeah. Yeah. You know, to a certain extent, data structure engineering is an art. Depends what's appropriate, what's not appropriate. Hash tables are good things. We've described hash tables are very good things, right? So for a lot of things, hash tables are the right way to maintain these kind of things. Any questions? Actually, at the risk of making it not more, hopefully making it clearer, but if not, maybe making it more complicated. Let me tell you a problem that happens in chess algorithms. Okay, you guys know about chess. We have programs that play chess. Programs that play chess search through all possible moves to a certain depth. Does everybody agree with that? Now, you could imagine if you have a chess program that has moved 4 levels deep. Maybe white moves its rook, black moves its pawn, white moves its knight, black moves its rook. Okay? And you get down to a particular state of the board. It was this. Each guy did 2 moves. You've got a different state of board. Does everybody see that? And if we search all possibilities from there, we can get a good sense as to whether this is a good thing to do, right? But what if we then had someplace else where we looked at black moved its rook, white moved its rook, black moved its bishop, and white moved its knight? Does everybody see that we might end up at exactly the same board configuration from a different sequence of moves? Does everybody see that? This is the case where the hash table idea is kind of important. Does everybody kind of see that? If you want to go through all possible board configurations and evaluate how good or bad they are, if I have already seen this configuration, okay, when I did it this way, I don't want to keep searching it deeper here. Does everybody agree? So you can imagine a chess program is going to have a hash table, probably, of states that it has visited and it has scores for. And when you search from another move's vantage point, if you get back to a state you've seen, you want to say, okay, I know how much that's already worth. I don't keep searching for it. How many people see that idea? That's really the idea that where the hash tables are kind of important. In certain complicated searches, maybe the same state should occur again and again. Okay? If so, you should store it to prevent it. Okay? And the kinds of problems I'm giving you in here, if you're smart, you never are going to need to construct the same state again. Okay? And so there's no need for the hash table type data structure. Any questions? Any more questions about backtracking before I move on? Okay? Keep playing with it. I think this is I find this a good exercise for people to do, because it really, programming, it gives you an idea of how it's really working. And if you are baffled by this, if you're scared, what do? Take my basic routines, generate all permutations without pruning. When you get to every permutation, count the length of the backtracking edge, of the longest edge, and keep the best permutation. Any questions? Then, once you've got that in hand, try to make it bolder and better. Any questions? Okay. So what I'd like to do now is to shift the gear to another topic that is, one of my favorite ways of designing algorithms, which is a trick called, a paradigm. I guess paradigm's a fancier word for trick, that called dynamic programming. And what dynamic programming generally is, if you want to know how you recognize a dynamic programming problem, I mean, they tend to appear a lot on problems where the state of what you're doing, where the objects that you're working on kind of have a left-right order to them. Okay? Character strings tend to have a left-right order to them, right? Permutations have a left-right order to them, right? Leaves of a tree, if you draw the tree on a plane, have a left-right order to them, right? So, and once you understand what dynamic programming is, I find it a very, very easy thing to do. Okay, Joe Mitchell, is the professor who's here before me. We have written a bunch of papers over the years. We spent a lot of time sitting at blackboards with a problem on there trying to find a fast algorithm. And we will stare at the blackboard for, 10 minutes, 20 minutes quietly. Then one of us will say, dynamic programming. And the guy will look at it and say, you're right. And that's the end of it. And why is that? It's because once you see the idea well enough, okay, it's very much of a mechanical thing. That said, there are a lot of moving parts that people kind of get lost in, okay? And so you need to see enough examples till the light goes on. That's the only thing that I can say. Any questions? Now, we did see an example of it when we talked about Floyd's algorithm for all pairs shortest paths. That was a dynamic programming kind of thing. And when I talked about, you may remember we talked about the problem of the day where we wanted the shortest path with exactly k edges. Remember how I did that? I kind of defined this recursive formula, and then I said evaluate that recursive formula. That is the idea that we're going to be using, okay? That we're going to be basically taking our problems and trying to write up recursive formulas for them and solve our problem by evaluating the recurrence. Any questions? Still should be foggy and mysterious, but let's take a look at it. Okay, so when you guys look at greedy algorithms were the kind of thing that like minimum spanning tree, where you took a, you said, I can always take the shortest, if I was Kruskal's, I can always take the shortest edge that doesn't create a cycle and add it to my tree. And I can keep doing that. And because of this magical proof, I can guarantee that I will always get the minimum spanning tree, right? That was the amazing thing about Kruskal's algorithm. If you were going to do minimum spanning trees, and I told you to do it with backtracking, could you guys find minimum spanning trees using backtracking? What would it be? You might want to write an algorithm that constructs all subsets of n-1 edges, right? And test to see if it's connected, and computes the sum and keeps the smallest one. Does everybody kind of see it? Okay? So you could do minimum spanning tree by backtracking. You need to have your head examined because you've got a much faster algorithm for that, right? But that's only because you have the careful proof. The correctness of the brute force backtracking algorithm should be obvious, right? I'm constructing all trees. Okay? I'm picking the minimum one. This has got to be the minimum, right? Now, what makes dynamic programming interesting is that it's going to be, in some sense, a form of exhaustive search. We're going to try essentially all possibilities. But we're going to use storing results to avoid recomputing. That's actually, when you think about it, what I just said this chess thingy was like, right? How did that chess program work to try to speed up the search? It had noticed that if we had a score for how good or bad this board position is, from doing a search down like this, if in some later search I need to ask myself, what's the score of that board position? I could just look it up from the table instead of recomputing it. Does everybody see that was the whole idea with this hash table? That's going to be the whole idea with dynamic programming, except that unlike the chess problem, we're going to be able to use it to prove bounds on how fast our algorithm. It's not just a heuristic that speeds things up, but it's really going to give us an analysis. Any questions? Okay, that's still foggy. Okay, let's start off talking about recurrence relations. Those of you who have had AMS 301 have probably spent a lot of time on recurrence relations. Is that right? How many people, do they do a lot of that in 301? Okay, good. Did you do, those of you who didn't, did they have recurrence relations in 215? The discrete math class? No, okay, never mind. What is a recurrence relation? A recurrence relation is an equation defined in terms of itself. So if we take a look at this thing, that's interesting. an equals an minus 1 plus 1 is an equation defined in terms of itself. It says that the nth value of the series is the n minus first series plus 1. Does everybody see that? This over here is an equation defined in terms of itself. an equals 2 times a of n minus 1. Does everybody see that? And this is another equation defined in terms of itself. an equals n times a to the n minus 1. The next term is the previous term multiplied by something, or added to something, or manipulated in some way. Does everybody see that? And you could have more complicated equations where the value of this depends upon a lot of previous terms. Okay? But a recurrence relation is a recursively defined equation. Now you guys know about recursion, right? What is recursion? You're used to writing subroutines that call themselves, right? A recurrence relation is an equation that calls itself. Okay, so it should be clear that they are analogous ideas. Any questions? What makes recurrence relations interesting for us, there's two things that will make it, well, more than maybe at least two things that will make it interesting. One is that recurrence relations are an amazingly rich language for specifying functions. Okay? Any polynomial can be expressed as a recurrence relation. What is the polynomial an equals an minus 1 plus 1? What is that? If we start out, let's say the first term is 1, what's the second term going to be? 1 plus 1 or 2. What's the third term going to be? 2 plus 1 or 3. Does everybody see that? So this recurrence gives us the function a of n. And in fact, any polynomial can be built up as a recurrence for it. Okay, there is some recurrence that will generate any polynomial. What does this recurrence equation look like? an equals 2 an minus 1. If we start a1 equals 2, what is a2 going to be? 2 times 2 is going to be 4. Does everybody see that? What is a of 3 going to be? 2 times 4 or 8. What is a of 5 going to be? 2 of, I guess, 8 times 8, which is 16. Does everybody agree with, see that? This recurrence defines the function an equals 2 to the n. How many people see this? I know this is looking, people getting, duh, I see this, okay? But realize recurrence relations are an amazing thing, because you can generate all exponentials, all polynomials, and weird functions. What is a weird function? What is the recurrence an equals n times a minus n to the a minus 1? If you start at 1, what is a of 2 going to be? That's 2 times 1. Does everybody agree, or 2? What is a of 3 going to be? 3 times 2, which is 6. What is a of 4 going to be? It is 4 times 6, or 24. Does anybody recognize what function that is? This I wanted to hear more excitement about. What is the function that is? N factorial, okay? Now why, but how weird a function is n factorial? If you think about it, the only reason it doesn't seem weird to you is somebody defined this exclamation point thing, right? What is 2.5 factorial? Okay, you don't know, right? So factorial is a weird function, okay? But it neatly is defined by a recurrence relation. And a lot of functions that we're going to be interested in are neatly defined by a recurrence relation. Any questions? The other thing that's good about recurrences is once you get good about thinking about things recursively, there is often a simple recursive expression for what you want to compute. You guys are supposed to have taken a bunch of courses on using recursion for programming, right? You should by now realize that there is often a recursive algorithm for something that is much simpler in some sense conceptually than the iterative version. And if you learn to look for recursive algorithms, that's like looking for recurrence relations. Once you get good at looking for recurrence relations, it's easy to find them. Any questions? Okay, good. Now, what is the mother of all recurrence relations? This is the Fibonacci numbers. Okay? Everybody has written a program to solve the Fibonacci. What is the nth Fibonacci number? It is the sum of the n minus first plus the n minus second Fibonacci number, right? This is the simplest recurrent. Okay, the basis cases were the 0th Fibonacci number is 0. The first Fibonacci number is 1. Why do people care about Fibonacci numbers? Anybody have any reason why they care about Fibonacci numbers? Yeah? So you're saying that there are data structures called Fibonacci heaps. Fibonacci lived in the 12th century. He probably didn't design them. So therefore, Fibonacci numbers must probably come into the constructions of them, okay? And that's I think, true. Why else do we care about Fibonacci numbers, yeah? They represent natural growth of something, and you're saying that you've seen this thing about pine cones. Has anybody seen the thing about pine cones? They seem to have pine thingies that are Fibonacci numbers, okay? Why is that true? Well, the way I think about it, this is the simplest second-order recurrence relation, right? You can't make a second-order recurrence relation any simpler than this. And therefore, you know, the way God designs the universe, the simpler equations tend to be described processes that are put in, that occur in lots of places. So that's why growth things sort of tend to get modeled by recurrence relations. Fibonacci numbers. Any other ideas about why you care about Fibonacci numbers? Okay? Yeah? There's this thing called the golden ratio. How many people have heard of the golden ratio? What is the golden ratio? You know, supposedly rectangles that look prettiest, okay, seem to have the property that they're 1 by 1.61. So what does that mean? If you're trying to be the person to design the first television set, what should your screen look like? You should use the Fibonacci, you should use this golden ratio. The Greeks used it in buildings and stuff like that. And somehow this ratio, as we will see, where the golden ratio really comes in, the golden ratio is the ratio of f sub n over f sub n minus 1 as n goes to infinity. Okay? So it's the ratio of successive Fibonacci numbers. They grow by about 1.6. Any questions? Okay. So that's why people care about Fibonacci numbers. Has anybody ever written a program to construct Fibonacci numbers? Everyone's written a program to construct Fibonacci numbers. Did anyone write a recursive program for constructing Fibonacci numbers? What happened when you did? Does anyone remember their experience? Yes. It was easy. But that's okay, but that's not the experience I wanted you to have. What was the other experience you had, yeah? If you made it big enough, you had a stack overflow, right? How big a number did you need for a stack overflow? Does anyone remember? By the time you hit 20 or 30 or something like that. Okay, any questions? What is the story of what happens when you write a recursive program to do the Fibonacci numbers? Does everybody see what's going to happen? To compute fib of 6, what's that going to do? It's going to recursively call fib of 5. Fib of 5 will call fib of 4. Fib of 4 will call fib of 3. Fib of 3 will call fib of 2. Fib of 2 will call fib of 1. Your recursive thingy said, if n equals 1, return 1. Does everybody see that? And this we can return. It would then say, call fib of 0. And that's going to be 0. It adds them up, and now I know fib of 2. I bop up to this level of recursion. It asks me about fib of 1. That's going to be 1. I now know fib of 3. I bop up to this level of recursion. It now asks me for fib of 2. Does everybody see that? And what is true in your naive implementation? You already computed fib of 2, but you didn't store it explicitly, right? Does everybody see that? And your simplest driven recurrence thing is going to go and compute, okay, fib of 2 again. Does everybody see that? And now to compute fib of 5, once I have fib of 4, I'm going to compute fib of 3 again, even though I computed this thing. Does everybody see that I'm doing a lot of recomputation? Right? I now, bop, 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 bop. To get this, I need fib of 4. I already had it, but I'm going to go compute the whole thing again. Does everybody see that? Okay. Any questions? What is the speed, what is the running time, the big O running time, of computing the nth Fibonacci number through this method? Can anybody figure this thing out? Yeah? You say 2 to the n. Why do you say 2 to the n? Okay, so that's not a terrible answer to say it's 2 to the n, because it's a tree that's going to have at most a height of n. That much we agree. And the branching is at most 2. Does everybody see that? So it is certainly at most 2 to the n. But is it actually going to be 2 to the n? See, there's hunks of this tree that don't exist. Isn't that right? So 2 to the n is an upper bound, but I'm not yet convinced that's the right bound. Okay? But I like that analysis. Okay? Any questions? Okay? What can I tell you? Well, what did we say about this golden ratio thing? Okay? We agree that the nth Fibonacci, there's this property that the ratio of the nth Fibonacci number to the one before it is phi, this 1.6 thing, which is this. This means that f of n is approximately phi to the nth, or 1.6 to the n. Right? Does everybody agree that the Fibonacci number is about 1.6 to the n? If we look at what's happening on this tree, to get that big number, it's being made of f of 1 leaves. Does everybody see that if you want to say how many f1 leaves are there to compute f of n, well, if we get a value of 13, that's because there's going to be 13 f1 leaves. 1, 2, 3, 4, 5, 6, 7, 8. Why is it that we only have 8 leaves here? Probably because I miscalculated what f of 6 is. I think it's that f of 6 is 8. Does everybody think, how big is the Fibonacci number, right? I think that's a typo there, right? 0, 1, 1, okay, 0, 1, 1, 2, 3, 5, 8. Does everybody see? This should have been 8 up here, okay? But my claim is that the big thing is that the value of the Fibonacci number depends upon is as many leaves as there are, okay, that are calls to F1, and that means 1.6 to the n. Any questions? So it should be clear the recursive Fibonacci program is exponential. Does everybody see it? Now, is there any possible way in the universe to make this program faster? Are we doomed to exponential computing of Fibonacci numbers? Okay, yes? Does everybody agree that a program that looks like this, okay, is in fact a faster way to compute it, right? What did it do? It started out with F1, F2. It kept F0 and F1. It computed F2. We keep F2 around. In order to compute, F1 to compute F2, we look up these values already. Maybe we store them in an array, right? The third value is the sum of the two previous ones. The fourth one is the sum of the two previous ones. Does everybody see that if we start evaluating this from small values of I to the n that we want, we will be able to fill in another Fibonacci number in one step, okay? And so now how much time does it take to compute the nth Fibonacci number? How fast is this algorithm to give us the nth Fibonacci number? N. Does everybody see it? This sounds better than 1.6 to the n, right? But what was the cost? There was indeed a cost here. The cost was space. We had to actually save the values of all these Fibonacci numbers here. Okay? So in some sense, we are using, as I wrote it here, n time, and if I keep the full array of Fibonacci numbers, n space. Does everybody agree? And you're saying, wait a second, I don't have to keep all n. I have to keep the last one, right? You're still using space to store a value, right? Now you're only using one lousy memory cell, right? But does everybody see that the key to doing this better was to save partial values? Yes?
Are you able to save more values to reduce time and save less values to increase time but reduce space? Like, is there a trade-off?
Okay, so in evaluating a recurrence relation, in general, there is, again, our goal is that in general in doing these things, we are going to want to save all our previous the results that might help us save time. Okay? Now, in some fancier world, maybe you might say, oh, instead of you saving all the values, maybe I'll only keep some of them and it'll get a little bit worse. In the problems we're going to look at, we're going to basically make it a rule to save all previous values if they can help us. Okay? And maybe like this, we're going to learn that only the last value is what's needed to help us, in which case we can then throw out the older ones. Any questions? Any questions about how the Fibonacci numbers work? Okay? This should be obvious now. Okay? Any questions? So, again, what is dynamic programming? If I need a definition, I would say dynamic programming is a technique for efficiently computing recurrence relations by storing partial results. Okay? Any questions? So if we think about what we've got ahead of us, we've got to design recurrence relations to do what we want, and we've got to evaluate them quickly by storing partial results. Any questions? Okay. Let's look at a, and again, the basic idea here is, and I keep saying this again, but basically the basic idea is that we're going to design a recursive algorithm, but cleverly in a way that it's going to reuse subproblems over and over. And if it does, then we can save these results instead of recomputing. Okay, that's the key idea here. Okay, let's look at another recurrence relation and go through the mechanics of how you would compute it. Okay? And this is something that you're probably familiar with. You should have seen somewhere along the line, called binomial coefficients. What is the binomial coefficient n choose k? Does everybody see that? That's n choose k. What is that thing? Has anybody ever had a course where you did n choose k? What is it? Yeah? Well, you're giving me a formula for it, but why do we have it? Why does it exist?
Because it allows us to find the number of subsets of something that allows repeats.
Basically, it allows n choose k counts the number of ways of picking a subset of k items from n items, right? Suppose you guys want to form a, you guys are angry about, let's say, how the grading is happening on the homeworks. And you guys, I say, form a committee of 5 of you. I won't talk to all of you, but form a committee of 5 of you, okay? How many possible committees are there that could have confronted me? Well, there's 210 people in the class. 210 choose 5 is the number of committees you could build. Any questions? So binomial coefficients are important because they count a lot of interesting things. How many ways are there to walk? Another example of binomial coefficients. You are in Manhattan, okay? Manhattan, as we know, is arranged on a grid, right? You are at, pick a place in Manhattan. What's a good place in, let's say the library on 42nd Street and 5th Avenue. Does everybody see it? This is 42nd, 43rd, 44th. This is 5th Avenue, 6th Avenue, 7th Avenue, 8th Avenue, 9th Avenue, and 10th Avenue. Conceptually, things like Park Avenue and stuff like that are given numbers like that, right? Does everybody get that idea? How many ways are there to walk from here to here, okay, that are the shortest possible path to walk from here to here? Does everybody agree? One way we could do it is to walk up like this and over. We could alternately go cha, 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 and over. Does everybody see that? How many ways are there if we have x blocks up and y avenues over? How many ways are there across that grid? So, yeah? You want to say x plus y, choose x. And why is that the right answer? Well, any walk you do is going to have x steps going up and y steps going the other way. Does everybody agree? So the path is going to be x plus y steps long, right? What makes a path distinct is which step on those paths represent upward moves. If we choose x numbers from 1 to x plus y, in this case, let's say we look at this path. The first step was an upward move. The second step was an upward move. Not the third, not the fourth, but yes to 5th, yes to 6th. Not the 7th, not the 8th, not the 9th, but yes to 10th. Does everybody see that if I pick as many upward moves as I'm going, the positions of my upward moves, the other moves are kind of specified by that. So this counts how many ways there are across the grid. Any questions? If you don't understand that, take a combinatorics class. Any questions? Okay? But what I want to tell you is binomial coefficients are a good thing. That's why you're being taught. They're a useful thing. Any questions? Yeah. Is that the same as 2 to the power x plus y? The answer is no. And as an example of that, suppose, let's say, that we have a different place, not Manhattan, but a deprived place, where all you had was 1 block long, right? How many places are there to get from here to here? It's obviously going to be only one way to get there, right? Even though x and y are long, so it can't possibly be that. Any questions? Okay. How do we compute binomial coefficients? You know about binomial coefficients. How do we compute them? Okay? Does anybody remember some kind of formula for them? Yeah? Okay. So everybody remembers this thing. Okay, does everybody remember that formula? That n choose n, what is it? What do you call it? N choose k is going to be equal to n factorial over k factorial times n minus 1 k factorial, right? I am going to tell you this is a terrible way to compute, okay, binomial coefficients. Why is this a terrible way to compute it? Okay, yes? You say because factorial takes forever. How much time does it take to compute n factorial? Well, if we live in a world of infinitely large numbers, it's just n steps. Does everybody agree? But do we live in a world of infinitely large numbers? Not in our computers, we don't, right? Does everybody see that? So suppose, let's say, what is, okay, 100 choose 99? Does anybody know what 100 choose 99 is? That's 100, right? If we were to compute it using this formula, 100 is something nice and easy. I can draw it on the board, right? What would this thing do? It would immediately compute 100 factorial. Does everybody see that? And then it would go and compute k factorial and do a division of things, okay? Yeah?
What if we were to store all the numbers 100 factorial on top and the bottom and try to like cross them out?
What if we store them and cross them out? Okay, now we realize this is complicated, right? Okay? Is there a better way to compute n choose k? Okay? The answer is in high school you learned a better way to compute n choose k. What was that? Does anyone remember? Yeah? Pascal's triangle. Does anyone remember Pascal's triangle? What was Pascal's triangle? Pascal's triangle, you guys say, yeah, I remember. You take this thing, and for every number you add up the two numbers above it, right? Does everybody remember that? So where does this come from? Well, one's on the outside. 3 is 1 plus 2. 3 is 2 plus 1. 1 is 1. 4 is 3 plus 1. 6 is 3 plus 3. How many people computed this, did a Pascal's triangle in their past? Okay, who did not have a Pascal's triangle in your past? Really, some of you did not. Okay, that's interesting. Okay? But what were you doing when you were computing Pascal's triangle? Why were you doing Pascal's triangle? Well, maybe it was to practice addition or something. No. In reality, what was it? Yeah? It gives you basically what this is doing, if you really want to know. This is 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 1, and 5 choose 0. I mean, 5 choose, wait, this is 5 choose 4, 5 choose 5. Any questions? What Pascal was really doing was computing binomial coefficients, right? And what Pascal was really doing was talking about this recurrence relation. If you think about it, what was this recurrence relation? I know that it looks like the light on the projector has burned down today. That's why I think it's less bright than usual. But what is this saying? N choose k equals n minus 1 choose k minus 1 plus n minus 1 choose k. Okay? Why is that? Is that really what Pascal's triangle is doing? Let's think about it. This, we said, was 5 choose 2, right? 5 choose 2 is 4 choose 1 plus 4 choose 2. Does everybody see that? And that over here, what is 4 choose 0, 1, 2, 3? 4 choose 3 is 3 choose 2 and 3 choose 3. Does everybody kind of see that? Implicitly, Pascal's triangle is basically doing this recursion. Any questions about it? Yeah?
So would this be O(n) times space?
Forget what it is now. Okay, not yet. Okay, let's just keep going here. Okay? Why is this recurrence right? We kind of agree that if we do Pascal's triangle and add these things up, we get a triangle and there are numbers in them. Right? Why is it that n choose k is equal to n minus 1 choose k plus n minus 1 choose k k? Does n minus 1 choose k? N minus 1 choose k minus 1. Why is that right? Yeah?
Also, you're going to have 4 i's
the first n minus 1, we will get n minus 1 choose k. If you only choose k minus 1, it means you choose the newest element. It means you choose n minus 1, choose k minus 1, and choose the new.
Okay, so to say that in a slightly different way, if this is counting on this side how many subsets there are with exactly of n with exactly k elements in it, right? My claim is that any subset of k items from 1 to n is either going to include n or it doesn't. Does everybody see it? If it does include item n, then there are n minus 1 items that we have, and we have to pick the other k minus 1 items from that. This is going to count how many subsets there are of k items out of n, where one of those items is actually the item n. Either this subset either includes item n or it doesn't. If it doesn't, it's drawn from the numbers 1 through n minus, all k numbers are drawn from the numbers 1 to n minus 1. This is counting all subsets which does not include n. This is counting all subsets that do include n. Any subset has to either include n or doesn't, so this counts all of them. How many people see why the recurrence is right? Anybody want a better explanation? How many people don't understand it? Okay? Let's think about how many ways there are to build subsets of, let's say, how many elements of subsets are there of the items 1, 2, 3, and 4 of size 2? Okay? How many pair items are there? My claim is that they are either going to be the subsets made from that do not include the 4th item, which is that, right? Does everybody agree? Or they are going to include the 4th item, in which case it's 1, 4, 2, 4, 4, 3, 4. Is there any other two-item subset that we have here that I didn't construct? So the number of ways to pick 2 items from 4 is the number of ways to pick 2 items from 3 plus the number of ways of picking 1 item from 3. That's what this is, right? This is the 1 item from 3 to pair up with it. This is why the recurrence works. Any questions? Okay. Any question about why the recurrence is correct? Okay, now we'll assume the thing is correct. What is good about computing, binomial coefficients by this recurrence? Does everybody see we're not constructing bigger numbers than we need to, right? We're not going to be constructing these, again, with a little bit of adjustment. We're not going to be computing anything we don't need. Okay, any questions? Okay, that's still just advertising for this. Big quick picture thing. Oh, I guess we still need to have basis cases for our recurrence, right? What are the basis cases of this recurrence to compute n choose k? Okay? Any idea of what basis we need? Yes? N choose n is 1 basis. What is n choose n? How many ways are there to pick 5 people when there's 5 people available? Well, everybody's getting drafted, right? So there's only 1 way to do that. Does everybody see that? Is there any other basis case we need? The way I look at this thing, one of these is working on the top, making the top smaller. And if we keep making the top smaller and smaller, it'll eventually, top will equal bottom, and that's going to apply. This is shrinking both of the top and the bottom. So what's the other case we need? Yeah? N choose 0 is 1. Does everybody see that? How many ways are there to pick 0 items? Okay, 0 items from n things. The claim is that there is 1. What is the 1 way to do it? The empty set. If you see that and you're happy with it, that's a great basis case. What would be another basis case that we are happy with that I do see? Yeah? What is n choose 1? N choose 1 is always n. Now this one, even I can understand, right? Because basically, if you're only going to pick one guy from it, there's n people you can choose from, right? Both of these could, either of these, this is in principle a little bit better, but basically both of them are fine basis cases. Any questions? Okay. Now, what I want to do, and this is kind of the important part, let's write a program to compute Pascal's triangle. Okay? How do you write, and because this is going to be a model of how we're going to do the bookkeeping in dynamic programming. Okay? So here is my, my program for doing this. And let's just see if we can figure this out. Let's talk about it, and let's see how this works. First, I'm going to set up a table, my binomial coefficient matrix, that is going to be the numerator, comma, the denominator. Does everybody see it? There's two arguments to a binomial coefficient, the top and the bottom, right? I am going to build a table that will store the value of the binomial coefficient xy for all x and y that I care about. Okay? Any questions? What am I going to do? I'm going to fill in my table according to the basis cases. What are the basis cases? Well, we agreed that the binomial coefficient I choose 0 is always 1. If we agree with that, we can now set all of those values to be set equal to 1. For all I from 1 to n, I choose 0 is 1. We also know that if x equals y, then the number of ways I choose j, I choose I is going to be 1. So for all n, the binomial coefficient for all j from 1 to n, BC of jj is equal to 1. Any questions about those initial conditions? Now, just like the triangle, I want to fill my triangle in, okay? And I want to do it, if you were doing Pascal's triangle, you filled it in by rows. Does everybody see that? Here, what I am now going to do is to have two nested loops. I goes from 1 to n, j goes from 1 to I. And what I am going to say is that BC of ij is going to be, as my recurrence says, BC of I minus 1, j minus 1, plus BC of I minus 1, j. Okay? Any questions? This is the recurrence from the formula. This is the initialization conditions. The critical thing that we need to understand is, are those loops the right loops to fill things in so that we have the items we need set up before when we need them? Okay? Any questions about that? Let's look at this. Any questions so far? Okay? Let's look at what this matrix is going to be. Did I give an uh-oh, trouble. Uh-oh, big trouble. It's good, but my hands are still here. Hold on. Let's try this again. Let's look at an example. Construct this example carefully. What does that array look like? Okay, and this I strongly encourage you to do by yourself, but let's go and do it. What should happen in our array? Let's say we have n go from 0, 1, 2, 3, 4. K, the denominator, okay, is going to go from 0, 1, 2, 3, 4. Does everybody agree? We have a matrix here that's an that's a two-dimensional matrix, right? What values here are the ones we're initializing? What is the first initialization step going to be? I choose 0 is going to be equal to 1, meaning I choose 0. I say that all of these guys are the ones that we're initializing here. Okay, this is one I want you to get the details right here. So I want you to look at this one. Okay? Does everybody agree that that is that initialization? And if I do something wrong, I want people to argue with me. Any questions? What is the other initialization that we want to do? Okay, yeah? Well, it says, is it a diagonal? Yeah, it does look like a diagonal. It says that for 0 up to n, all of these are going to be 1s. What does that mean? This one is a 1. This one is a 1. This one is a 1, and this one is a 1. Does everybody see that? Now, what are we going to fill in? Right? So let me just get, this one isn't here. This, just to make sure, is a first-class 1. And this is where we are sitting now, right? Let's say, which binomial coefficient do we want to compute? Let's say we're going to be particularly interested in 4 choose 2, right? Okay. How are we going to go and compute that? Well, what's going to happen here? First of all, the numerator is going to go from 1 to n. J has to be less than 1. So if we start out with 1, the only value of j that is interesting is 0. Is 1, 0 have a value? We already have that one, right? So we're not going to do that. Okay? Now let's have the outer one go. Suppose the inner loop now is going to, okay, so now let's say we finished that one. Now when I equals 2, what are we going to do? If I equals 2, we are going to be interested in j minus 1. Does everybody, j equals 2 minus 1, we are going to be interested in this value. Does everybody kind of see that? Because this loop in here is going to go, if I is equal to 2, this is going to be all values of j less than 2, which right now is really only 1, right? Do we have the 2 values that we need so far? What are the values we need? I minus 1, and then the values of j. Well, certainly if we're working on the value on the row I, we already have the values for I minus 1. Does everybody kind of see that? So now we add them together and get a 2. Does everybody see that? And now we are sort of done with that, right? Now we bop up, and now I is going to be equal to 3, and j is going to go from 1 to 2. 3, 1 is going to be adding this plus this. That's going to be 3. Does everybody see that? The next one is going to be adding this plus this. That's going to be a 3. Does everybody see that? I now goes to 4. It's going to be adding. The beautiful thing is to see that exactly the values we need are already sitting there. That was the beautiful thing in how we're evaluating it. Okay? And so this is going to be 4. This is going to be 6. And that is where, we, if we really cared about it, we would stop now. But if not, let's just fill in the table. Okay? And once we have this table, if you want to know what n choose k is for any n and k, it's sitting there. Any questions about this evaluation process? Okay? Any questions? Okay? This is one I want you guys to think and look at, okay? Because this is the mechanics of how you implement a dynamic programming recurrence, okay? Recognize that in dynamic programming there's a few different ideas going on. One is, how did we discover this recurrence relation? Well, if we were Pascal, Pascal discovered that recurrence relation, right? That's a thinking thing. But what I'm showing you here is another important thing, which is that once you have the recurrence relation, if you evaluate it in the right way, The items that you need are waiting for you. And the only cleverness in this implementation is how did we set up these loops, okay, so that they filled in the elements that we want. Any questions? Okay? Yes?
So are these typically going to be done without recursive calls, or are you going to have that?
Now, what? Wait. One thing you said here is notice. Look, there's no recursive call anymore, and that's exactly what we're doing. We are replacing the recursive calls here by looking things up in arrays. Does everybody see that? So we took this fancy recurrence thing, and we got rid of the recursion. Okay? And that is, generally speaking, exactly what we're going to do. Recurrence things, bad things can happen. They blow up, exponential, nightmare. Iterative thing, we're going to know we have a certain number. What's the running time of this algorithm now to compute n choose k? What is the running time of it? I can give you an actual, count it. How would we count the running time of this thing? The way I think it's the number of boxes that we're filling in times the cost to fill in each box. How many boxes are we filling in here? Yeah? You said n times k? I guess n max times k max, I guess, is true, okay? I would have said usually k max is the same as n. So I think of this as an n squared boxes, right? Okay? But yeah, let's say n times k. N max times k max. Okay? How much time do we spend filling in each box? O of 1, right? Because it's just looking up two items and adding them together. So this is n squared times 1, which is n squared time. Does everybody see that? Okay. Think about this. Get the mechanics of this right, because if you get this in your head, then we can worry about the complicated stuff. But you have to get the bookkeeping done right. Thanks for your attention. See you guys next time.